Today we'll be discussing how to evaluate limits analytically. Normally, whenever we're evaluating a limit, given any constant and a function, we can have direct substitution from the constant into the function, and most limits can be solved as simply as direct substitution. Some other basic limits can be found as simple as the limit as x approaches a constant with a different constant. The limit will equal the original constant presented in the function. Some properties of limits, such as scalar multiple, sum, difference, product, or quotient, can easily be solved by having, for example, the scalar multiple. It will have a constant multiplied by a function. This will equal the constant multiplied by the limit of the function. Others, such as a function adding or subtracting by another function, will be equal to the two functions given direct substitution, add or subtracted by each other. With products and quotients, we can have two functions multiplied into each other, and it will equal the two of them multiplied into each other with the direct substitution of the constants. Or when presented with a quotient, as long as the denominator does not equal 0, it'll be just as simple as before. They'll all be equal to themselves given direct substitution. Again, so long as the denominator does not equal 0. How to evaluate a limit given a function with a radical such that n is equal to a radical. We can evaluate this simply as n into the constant, direct substitution. This will be true for all limits when n is odd. This will be true for all constants. However, when n is even, this will only be true when the constant is greater than 0. And as we can see with this example presented in the slides provided, we'll have a limit as x approaches 3 radical 3 times minus 10. So when finding the limit of this, we can find the limit of just cx, whatever the function is on the inside. So just as we saw before, we can find the limit as x approaches 3, 2x squared minus 10, which will then be translated into 2, 3 squared minus 10. 3 squared will be 9, times 2, 18, minus 10, 8. So now plugging all that back into here, we'll be looking for the limit as x approaches 3. Concluded it will be 8, and this is going to be the value that we find for the limit as it approaches 3 radical 2x squared minus 10. Limit will be 3/8. Because at this point, this is now a constant after evaluating the original function. And as we know, the limits of a constant will equal its constant. Another theorem that we can present will be evaluating the limits of trigonometric functions such as sine, cosine, tangent, secant, cosecant, and cotangent. All of them will apply to the same rules. Any single one that has a limit to a value will just be equal to itself using direct substitution. At times, we're going to find limits with functions where at all points except 1, the limit will be continuous. However, we can also find this limit by evaluating what the function originally is. So in the example provided in the slides, we have the function of x cubed minus 1 over x minus 1. As we can, if the limit as x approaches 1, x cubed minus 1 over x minus 1. As we can see, when we do direct substitution into the x's, the denominator will be 0, and then we'll present a function that will be undefined. So what we can attempt to do is change the function by evaluating if we can factor the top, such as x minus 1 times x squared plus x plus 1 over x minus 1, allowing us to remove both ends and give us a new function of x squared plus x plus 1 being the same function similarly, because all we're doing is removing what's already there and simplifying it. However, they can be described as function g of x. In this function, if we evaluate the limit as x approaches 1, we will see that there is no time, there's no point on this graph on which the interval breaks. And with g of x equaling f of x, it also proves that the limit of this function, the original function f of x, x will be able to equal the exact same value that we find on the limit as this function. Let's work out the math on that so we can prove it. So with the original function as x approaches 1, we can clearly see that this will be equal to 1 cubed minus 1 over 1 minus 1, which is just 0 over 0. This is an undefined point. However, the limit as x approaches 1 of x squared plus x plus 1 presenting the g of x that we had just broken down, it'll be equal to 1 squared plus 1 plus 1, which is equal to 3. So how can we prove that this and this will be equal to the same thing, the limits? Well, if we find the limit as it's approaching 1, we can use how we can find out that these two will equal the same limit is that we can start using values that are close but not equal to the limit. So values such as 0, 2, 1, you can have 1.5, 0.5. And as you get closer and closer to the limit, you'll see a pattern of it approaching a very specific point. So if we were to do it by 0, it'll be -1, -1, it'll still be 1. We do 5, it'll still be 1. 0.75. After evaluating at 1.5, we'll get 4.75, and at 2, we'll get 7. So we need to continue finding closer and closer values in an attempt to get as close as possible. We will do 1.001 and 0.999. Using these two values after evaluation, we will get 3.003, etc., and 2.997, etc. Because we will never have a defined value here, we can tell by the graph that they're both approaching 3. Being as close as possible, we will continue reaching without actually touching 3, which presents us with a limit of 3 on an open interval on the graph. Presented this way for this function. Essentially any form of algebra that we can use to find to break down a function that equals 0 or is undefined, and we can find a way to present it with a real value, whether if it's being used with rationalizing, finding ways to factor out certain polynomials or just different functions to break them down so that they don't equal 0 when the denominator is at 0, such as like any polynomial. We can find a way to prevent this from equaling 0. We'll be able to evaluate just about any limit. One last concept that we can present today would be the squeeze theorem. When we have multiple functions such that need to have their limits presented, f of x, g of x, h of x, all splayed out on a graph, we have a way to determine if all of them have the same limits on a very specific point. So say that f of x is greater than g of x. This will present as f of x on all points of x in its limit, that h of x is less than f of x on all points of its limit, and g of x is both greater than h and less than f. The point in the center being the final limit, whether if it's undefined or not, is considered the squeeze theorem, because as things get closer and closer together, there will be a point where all three of them touch. That will be all for the presentation. I hope that everything was informative